Okay, so in your lab, you had a meter stick, and you had it pivot at the middle on 50 centimeters. You placed a small mass, let's say M1 on one side. You placed a larger mass, let's say M2 on the other side. You measured this distance to be D1 and this distance right here to be D2. Now, as I walked around, I saw lots of similar relationships, and that M1 D1 was equal to M2 D2. Now, what we didn't include was the fact that there's actually a weight acting on this meter stick. So if you add G to both of those masses, it begins to look like a force diagram because we have the weight of one mass and the weight of the other, which means we need to stick a G in here and a G in here, and that gives us that M1G D1 is equal to M2G D2, where this looks like a force. Now, if I removed this force right here completely, then I would have to apply a force on this side over here to keep it down. So you'd have to apply a force in that spot to keep the system in equilibrium. So this means that if you look at the system, then you can write this as being a force at a distance. Now I'm going to use an R1 instead of a D1, and F2 R2. Now, mathematically, that means that F1 R1 minus F2 R2 is equal to 0. And this is actually the sum of the forces, the sum of the torques, actually, acting on the system. Now, when you were determining the mass of the meter stick, so you had your meter stick, and now it was being pivoted down here on the end. You added a mass here, and the object, the meter stick, stayed balanced. So it was in equilibrium. Now, the center of mass, the center of the meter stick, is where the weight of the meter stick, so FG meter stick, was applied. So then in summing the torque, or summing up the system here, it was in equilibrium. So the sum of the torque is equal to 0. And effectively your M1G R1, so this mass at this distance, minus the gravitational force acting on your meter stick times this distance here, I'm going to call it R2, was 0. So hopefully you found that the mass of your meter stick, which is buried in here, would be M1GR1 divided by R2G, and that should be the mass of your meter stick. Now, what is this torque thing? This torque thing is the force that's applied at a particular distance from a pivot point. So let's look at what torque is. Torque would be the force that's applied times the distance. And that works if this force right here is perpendicular to R. So what does that mean? That means that when you have an object like this, and here was your pivot point, and you hung a mass from this end over here, the angle between this force and this arm is theta. There's that angle right there. And it's perpendicular. Now, it doesn't always happen that the force is perpendicular to the arm. Like when you hold the door open for someone and you're trying to stand out of their way, you have to reach and apply a force to the door, and that angle is no longer perpendicular to the plane of the door. So when we are calculating that, we need to take into account that the force we apply is not always perpendicular to the door. So imagine this is the door to the classroom. There are hinges over here on the right side. The doorknob is here, so you're looking down on the door. Now, if you were to swing this door open so that now the door is oriented like this, it's open to the hallway. So here's the door handle. We're still looking down on top of it. And you're trying to hold this door open for someone. So you're applying a force. So you're standing in my classroom. And you're applying a force, and it's almost parallel to the door because you're trying to hold it open for someone else. Well, the only component of that force that you're applying that's actually causing this thing to rotate is that component that is perpendicular to the door. So when you apply a force, you're pushing it over and over. And it's this one that is applying the torque, or the force component is applying the torque. So I need the angle that this force is being applied. And usually we do the angle to the door. We're going to call that theta. So if you remember from your trig, the force like this, if you have an x component and a y component, and this is theta, and you want to find this opposite side over here, this would be the perpendicular, the force in the y direction right here. Fy was equal to F opposite is sine theta. So to be most general, the torque is equal to F perpendicular to R times R. Or, to write it specifically, the torque would be F sine theta. That takes into account that it may not be perpendicular to the door. So not all forces are applied perpendicular to the distance times R. Now you'll see this written most of the time in textbooks as FR sine theta. Now let's look at units here. So if we look at our units, torque is FR sine theta. Torque itself is TORQUE. This is the force applied. This is the distance from the pivot point. And this is just the angle here. between F and R. Look at your units. Force is measured in newtons. Distance is measured in meters. So that means that your torque should be measured in newtons times meter. Now I know that that looks like a joule, but because torque is a cross product, truly torque is F vector crossed with R. And for those of you that are in calculus, you may know that this is the same thing as FR sine theta if you're trying to find the magnitude. Work is the dot product. If you remember that from math, this is not a prerequisite. You might remember that from math, that the force what a dot product is. And that does end up being, but it's FR cosine theta here. The unit for work is a newton times a meter, which we call a joule. And we call it a joule because technically our unit here for torque is newton meter, and we don't want to get these two confused. So this is a newton meter, and then it's the unit for torque, where this is the unit for a joule. That is your unit, or unit for energy. This is your unit for torque. All right, now let's look at a couple of applications beyond our lab with torque. So just like any other system that we've summed forces on before, torque is kind of a rotational analogy for that. So let's say you've got a system like this, and your pivot point is here in the center, and maybe we're going to apply a force at the very end with a magnitude of 10 newtons, and we want this thing to not rotate, and this angle is like 30 degrees here. And you want to apply a force somewhere on the other side so that it stays balanced. But you're having to apply this force maybe at this position. So let's say that this is 1 meter away. This point right here is 0.25 meters away. And we know that this force is at an angle of 60 degrees. Now when you look at this system, we have to kind of notice if this is where the pivot is, this force right here would tend to make this thing want to spin that way. And but this force over here would tend to make it want to spin in the opposite direction. So as we're summing our torques, we can use these directions for positive and negative. And let's say that we consider this to be the positive direction and this to be the negative direction. Just pick something and go with it and be consistent and you'll be fine. So then I have a force of 10 newtons at a distance of 1 meter at an angle of 30 degrees to the arm. So 30 degrees to the arm right there. And then in the opposite direction, I have an unknown force. I'm just going to call it F. An unknown force at a distance of 0.25 and times the sine of 60 equals 0. Ran out of space. Okay, so if we solve this, we'll have 10 sine 30 is equal to F times 0.25 times sine 60. And then the force should be around 23 newtons. And that's the force that we would need to put in up here at this angle and at this distance to put this system in rotational equilibrium. Now let's look at another one. Let's say you have a system and there are some forces acting on this rod, and maybe you've got a pivot point here at the side, and you apply a force this way. So maybe this is 10 newtons, and this is 60 degrees here, and you want to find the torque on this system due to this force. And your rod is 1.2 meters long. Then you'll have the force times the distance times sine of 60. That is, the torque is equal to F(r) sine theta. So when I do my calculation, I get 10.4 Newton meters. But another way you may see this type of problem written, you've got a arm, and let's say the pivot is still over here on our side. A lot of times we label the pivot or the pin with a P, so that would be your pivot point there. And now we are going to apply a force to this arm, and we have this angle right here is 60 degrees, and this force is maybe 6 newtons. And the distance from the pivot point to this point right here will make 3 meters. So then what is the torque on this rod about the point P? That's the question. So now let's look at it. This 60 degrees, though, you have to be careful. This 60 degrees is not the measure of the angle between the force and the arm, but it's between the force and a line perpendicular to the arm. So we have to be careful. So you can extend the arm out, and then this would be 30 degrees. And you can continue and do that the torque is equal to F(r) sine theta. So F(r) sine 30 degrees, which looks like it is 9 Newton meters. All right, one example. Let's look at, instead of having a bar, what if we have a wheel? Maybe this is like gears. You know, your bicycle has these different levels of circles. Pretend like those are pretty. And the chain is applying a force out here. Maybe here's F. And maybe that force is like 10 newtons. And then on the inner spoke, or the inner gear here, maybe we have another force F. And we want to find that force maybe. And let's see, this outer radius right here, so just looking at this outer radius, that's, let's say that is about 0.5 meters. And then we can say this inner radius is about 0.25 meters. So if I wanted to find the force, the output force, or the force that we'll get when we pull on this big circle with this 10 Newton force on this smaller inner circle, then I can use torque to find the force. So if I sum the torque and it's balanced, then I can find what force that we need here. So the 10 Newton force is acting at 0.5 meters, and the unknown force is acting at 0.25 meters. And that's all. And they're acting in opposite directions, so I put a negative in front of one of the forces and an understood positive in front of the other one. So now we can solve for the unknown force. And that would be half of 10 is what, 5 is equal to F over 4. So with the force applied be 20 newtons.